we have 4 really interesting papers. The first one is goal-oriented multimodal interactive recommendation with verbal and non-verbal relevance feedback. Just a quick introduction of this paper. This work proposed a novel goal-oriented multimodal interactive recommendation to incorporate the user preferences from both verbal and non-verbal feedback over time. The presenter is Yak-Seong Hu from University of Gazelle. Please, let's start.
Okay. Thank you. I'm Yak-Seong Hu. Today I will present our work, goal-oriented multimodal interactive recommendation with verbal and non-verbal relevance feedback. This is joint work with Craig MacDonald and Iad Wunis from University of Glasgow. So multimodal interactive recommendation is a type of information-seeking task that aims to elicit the user's dynamic preferences from their multimodal interactions and recommend items according to their current needs through multi-turn interactions. In the previous work, they usually focus on verbal relevance feedback. So in this paper, we consider to leverage both verbal relevance feedback and non-verbal relevance feedback in the multimodal recommendation task. So in this paper, multimodal interactive recommendation is specifically concerned with a goal-oriented sequence of multimodal interaction, such as images, textual feedback, and likes and dislikes between users and recommender systems. And interactive recommendation tasks have been typically formulated using deep reinforcement learning approaches with Markov decision processes and partially observable Markov decision processes by maximizing the cumulative rewards. However, the recommendation policy optimization processes of the existing deep reinforcement learning-based models are associated with implicit multimodal representation learning, which is usually called coupling of policy optimization and representation learning. So here is a use case. The user, in this use case, the recommender system needs to encode the images and the user's natural language feedback into multimodal representations. And it also needs to compose them together. And in the previous model, they just concatenated them together as a composed representation at each turn. And it also needs to consider to track and estimate the recommendation policy, the user's preferences with recommendation policy over time. But in this use case, we can find that it's very difficult to get good representations of composer representation or textual or image representations with the implicit learning with recommendation policy laws. But the deep reinforcement learning approaches requires good representations to drive the recommendation policy optimization process. So it's typically challenging to optimize the agent to improve the recommendation quality associated with the coupling issue in deep reinforcement learning. So to address the coupling issue, we propose a novel goal-oriented multimodal interactive recommendation model that uses both verbal and non-verbal relevance feedback to effectively incorporate the user's preferences over time. And in this architecture, we can divide this model into 5 stages. So in the first stage, we need to pre-process the recommendations and corresponding textual and corresponding verbal and non-verbal relevance feedback. And we store the disliked items in the negative feedback history. And in the next stage, we encode the liked items and the corresponding natural language critics with clip visual and texture encoders. So in the following stage, in the third stage, we consider to compose them together rather than just concatenate them together. So we directly adopt a composition network called textual image residue gating network. So it produces two types of features. The first one is called a gated feature, which can be considered as the reference of the user's preferences. And the below one is the residual feature, which can be considered as the modification of the basic reference feature. So this process is very similar to the image revising process. And in the next stage, we adopt a transform encoder to estimate and track the user's preferences over time. And in the final stage, we match the candidate items as the recommendation, top K recommendations. So due to the goal-oriented nature of the multimodal interactive recommendation task, we formulate the task as a goal-oriented, partially observable Markov decision process with verbal and non-verbal relevance feedback for top K recommendations. In this figure, we can see that the interactive recommendation process decomposes the long-term hard-reaching goals into easily obtained sub-goals expressed by the user's natural language critics, and also with the likes and dislikes interactions. Therefore, our proposed Gaussian model with GAU-POM-DP can pursue their own goals, such as the user's desired items of the user's critics for acquiring their desired items, and learn to achieve their goals while goal-oriented rewards. So different from the traditional reinforcement learning with MDP and POM-DP, the goal-oriented rewards in this paper are calculated based on the distance or similarity-based values between the action and the goal. So to optimize our model, we propose to adopt two stages learning approaches. So in the first stage, to improve the sample efficiency of the following deep reinforcement learning stage, we initialized the Gaussian model with a supervised pre-training process instead of using a random initialization. So in the pre-training stage, in this loss function, it consists of two parts. The first part is the supervisor triplet loss for recommendation policy, and the second part is the composition loss for the representation learning. So we aim to score the dialog state for target item higher than dialog state with negative item. And we also aim to score composed representation for the target items higher than the composed representation for negative items. And in the fine-tuning stage, we directly replace the triplet loss function with the goal-oriented policy optimization with reinforcement with the reinforced approach by maximizing the cumulative goal-oriented rewards across multiple interaction turns. And we keep the second one the same as the pre-training stage. To leverage the benefits from the non-verbal relevance feedback, we iteratively consider random sampled items from the previous disliked recommendations as hard negative samples, and we also learn from rewards on the both liked items and the disliked items. So to perform the experiments, we adopt 4 data sets, the shoes data set and fashion IQ dresses, shirts, tops, and tees. And we also compile our proposed model with various baseline models, such as interactive recommendation models with single modality or textual image retrieval models and multimodal interactive recommendation models with supervised learning approaches and reinforcement learning approaches. So the success here is measured by getting the target image in less terms, such as using the success rate and ranking it more highly at given terms, such as NDCG at 3 and NDCG at 10. Following the previous work, we also adopt a user simulator for training and evaluation. So this user simulator can give both likes and dislikes on the recommended items, and it can also provide a natural language critic to describe the attributes missing from the liked item. And here is a demo to show how the user simulator generates the sentence given the candidate item and the target item. So the first one is the target item, the second one is the candidate item. So it produces the same design but are brown. For the first research question, we investigate the performance of our Gaussian model compared to the baseline models. So here I just show some results based on the shoes data set by comparing the recommendation effectiveness at various interaction terms with top 3 recommendation. So in the figure, we can observe that our proposed model can achieve overall better performance than the previous mentioned baseline models across different interaction terms. And we also checked performed a significant test at the 10th interaction term. So we find our proposed Gaussian model achieved significantly better performance at the 10th term than the best baseline model across all metrics. And more details and data can be found in our paper. So for the second research question, we try to investigate the impact of the components in our Gaussian model in terms of both composition representation learning and the goal-oriented policy optimization. So let's have a look at the figure on the left-hand side. It tells about the impact of composition representation learning on the shoes data set. So if we remove the composition network and its components, and so we can find the performance are degraded. And if we remove the composition loss in the pre-training and fine-tuning stage, we can find they'll also decrease. So compared to the Gaussian model. So our proposed Gaussian model can benefit from explicitly learning the composition representation with advanced component network, such as the TIRG. And in addition, we also perform application study on in terms of the goal-oriented policy optimization. We removed the hard negative sampling by just randomly sample items from the candidate pool, or remove the goal-oriented rewards in the loss function, and we can find that the performance of also decrease. And so our proposed Gaussian model can also benefit from optimizing the recommendation policy with hard negative sampling and goal-oriented rewards. So to consolidate the results shown in the previous slides, here we show a use case. So we can find that our Gaussian model can only needs 2 interaction terms to get the target item, but the best baseline model like DRs require 3 interaction turns to get a target item. So in conclusion, our proposed Gaussian model can significantly outperform the baseline models, and it can also benefit from the explicitly learning of the composition network and both verbal and non-verbal relevance feedback. And we also perform other ablation studies, like using different hyperparameters, like various discount factors, and different numbers of top K recommendations. So if you are interested in this work, you can find more details in our paper. So for the future work, we consider 2 points. The first one is about personalized recommendation using parsed shopping history. In this work, we just consider randomly initialized recommendation at the first attempt. But when we usually people can have some past shopping history, so there should be a kind of trade-off between past users' interest and the current needs. So it might be challenging to balance this kind of trade-off. And in the second part is we consider to use large language model powered autonomous agents for this task. So I think this can be an inspiring and promising direction, because it can enhance the multimodal interactive recommender system with some abilities like memory, reasoning, and planning, etc. So I think that's our consideration for the future work. So that's all for the talk. Thanks. If you're interested in our work, you can read the paper, and if you have any questions, you can contact us through the email and the Twitter. Thank you.
Thank you very much for your very interesting presentation. It's time for questions. Okay, there is a question from the online audience. How many textual feedback items needed for training to achieve these results? How many textual feedback items needed for training to achieve these results?
Actually, we perform experiments with 20 turns in our experiments, and we achieve this kind of experiments. And that at each turn, the user just provide short sentences as the natural language critics about the presentation, about the recommendation. Yeah.
Okay, thanks. Any other question?
Hi, I have a question. So,
okay, please.
Looks like you did some active learning / reinforcement learning simulations with simulated user feedback. But in the abstract, you also mentioned that there is a coupling of policy optimization and representation learning. So can you elaborate on this message? What do you actually mean here?
You mean the coupling issue in this paper?
Yeah.
Yeah. As I mentioned in this figure, so if you want to learn a good policy, you need a good representation, like the image representation, texture representation, and also composition representation. But it's very challenging to learn good composer representation with recommendation policy laws. So because you don't, it's a kind of implicit learning process. But if you want to learn good policy, here is another direction. So you cannot, so this is a coupling process with implicit representation learning and policy optimization.
Thank you. Did you employ any kind of prior information on the representation to help decouple these effects?
You mean to represent the original imagery and the textual language?
Yeah.
Yeah. So here we adopt the pre-trained clip models. It provides a unified multimodal representation things, and like the clip visual encoder and the clip texture encoder. So it can provide a good foundation for the representation. And we also adopt a linear layer and a norm layer to further fine-tune it. Yeah. And also in this stage, we use the TIRG component to then compose the representation. Yeah.
Thank you.
Yeah.
Thank you. So I have just a curiosity about your model, since I work with conversational recommender systems. So do you know whether this model is, in your opinion, exploitable for conversational recommender systems?
Yeah, actually it can be considered as a type of conversational recommendation because there are multiple tense natural language feedback. But in general, we just, in the existing research, they just formulate conversational recommendation as question-based. So here is the critiquing-based inductive recommendation. So as I mentioned, we are considering to leverage the large language models powered autonomous agents. So if we have this kind of pre-trained large language model, we don't need to train the transforming encoders from the scratch, and you can better understand the user's questions and also ask some clarification questions in the conversational process. I think this can be more powerful and a promising direction. Yeah.
Okay, thanks again.
Yeah, thank you.
Let's move to the second paper.